Okay, so hi everyone. My name is Sharon. I'm here to tell you a great story about one of our vulnerability research journeys we had. So let's start with a quick introduction on myself. First of all, I'm very happy to be here in person, not online. We saw what happened when we're trying to connect through Zoom. So I'm Sharon Brizinov. I'm a vulnerability researcher at Claroty. We're doing a lot of vulnerability research on mostly SCADA and IoT equipment. You can see here our great lab. This is my playground, as I like to say. This is where I spend most of my time. I'm breaking stuff, trying to build stuff, trying to research, and try to get into the attacker's mindset in order to find vulnerabilities. So today's story is about a vulnerability we found many years ago. Not many, but at least 3 or 4 years ago in an EtherNet IP protocol stack. So we found a vulnerability in an Ethernet IP protocol stack, one of the implementations in one of the vendors, and we disclosed it to the vendor. And the vendor fixed the issue, but then we figured there might be other stacks or other vendors implementing this stack that are vulnerable as well. So it started when my boss came to my office and told me, okay, look, we have lots of customers owning Opto22 SNAP PAC platform, and I want you to perform vulnerability research on it so we make sure it's safe and secure. So obviously, this is what I do. This is what I love. I started to reverse engineer. I started to get myself familiar with this platform. So I went online. I went on eBay and purchased this platform. Now, Opto22 SNAP PAC is a PLC, is a modern PLC, a great one. It is being used across many industries, including manufacturing and production. And I started to read the manuals around it. In the manuals, I saw there are different modules, CPU modules. So I just picked one. I picked randomly the SNAP PAC R2. The CPU's modules are differs one in each other by how many resources they have. So how many RAM, what is the size of the hard disk, etc. So it doesn't really matter which one I picked. I picked this one. And I started to read about the CPU. I downloaded the firmware and I wanted to analyze it. But in order to analyze a firmware of unknown device at the time, I did not have this device. It was being shipped from, I don't remember where, maybe Asia somewhere. And I wanted to understand the architecture of the CPU. Soon enough, I went to the vendor specification page and I figured that we're dealing with a cold fire CPU. So NXP cold fire origins is a microprocessor that origins from Motorola 68K family architecture. So we knew, or at least I knew, how to reverse engineer right now because I had the instruction set of the Motorola 68K. I plugged the firmware into JIDRA and IDA and started to reverse engineer. And I asked myself some leading questions, some leading research questions. For example, what is the attack surface? What potentially attacker would do in the network if they encounter such a device? So I listed all the supported protocols that I gained from my knowledge into the firmware from the vendor's website and from the specifications. And I decided to focus on Ethernet IP. So this is a great protocol stack that I had some familiarity with, and so I decided to start with it. Now, in order to find the vulnerability in a protocol stack, specifically the Ethernet IP, obviously we need to get ourselves familiar with this protocol. What is this protocol? What is being used for? Where it is being used, etc. So I started to gain some more information about this protocol. And Ethernet IP is a protocol being developed, maintained, and developed by OVDA organization. This is a great organization with, I think, more than 300 companies involved in this project, and they're developing both the specification of Ethernet IP and the CIP, the Common Industrial Protocol. The The goal of Ethernet IP, if I'm being broadly and generic here, is to transfer CIP, Common Industrial Protocol, over the network, over Ethernet. And CIP is a communication protocol that is being used to share automation data between devices. It is a great protocol being used in many, many vendors in the devices, mostly Rockwell adopted Ethernet IP and CIP. And these protocols are running together, CIP over Ethernet IP, just like a transport layer, over TCP and UDP over port 44181. So who's using Ethernet IP and CIP? Apparently many devices. Not sure if you are able to see the text here, but there are different modules from different vendors. Rockwell is a great example for that. Most of Rockwell devices, if not all of Rockwell automation devices, are using CIP and Ethernet IP. And the way I got this pie chart is by just going on Shodan, the great search engine, and I searched for port 44181, and Shodan implemented the Ethernet IP protocol in their scanners, so they're able to gain information. Now, what information is being returned from Ethernet IP? One of the functions is list identity. So list identity is one of the built-in functions in Ethernet IP, and it returns information about the device. For example, the firmware number, the module, serial sometimes. So Shodan actually implemented this protocol, which is quite simple to implement. And they're just sending a lot of requests over the internet and collecting all the responses and parse the data, and they show what kind of devices are using Ethernet IP. That's how I was able to collect and compile the list I showed. Now, one of the features, as I said, Ethernet IP is being used to transfer CIP data. So one of the functionality of CIP is Forward-Open. Forward-Open allows users or engineering stations to communicate with a nested device. So let's say you have multiple devices that are all support the CIP protocol. You can chain them in a way that one device will be nested behind another one. And using some specific request, Forward-Open request, we can compile a path, they call it a CIP path, to communicate with a nested device. So if your network is very structured and complex, you can use this Forward-Open functionality to communicate with a nested device in your network. So I knew that this is probably the most complex feature of CIP, so I decided to focus on this in the firmware that I researched. And here you can see how it looks like when we're parsing it with Wireshark. So Wireshark has a dissector for both Ethernet IP and CIP. So you can see here, there is one byte that says how many words are 2 byte pairs, are constructing the CIP path. And in green, you can see actually the CIP path that tells the devices along the way how to redirect the packet through the CIP network. So I decided, as I said, to focus on this feature. It's a complex feature if you'll think about it, to route packets through a dedicated protocol. It's not that easy to implement. And quite fast, I discovered a bug or a vulnerability in the firmware that I researched. And the bug was that the specification does not limit the amount of words or the amount of CIP path behind 1 byte size. So in 1 byte size, we can have from 0 to 255 options, or in our case, up to 255 words that describe the CIP path. So it means we can have quite large of a CIP path to work with. But in the firmware that I researched, for some reason, I think for memory limitations, they limited this number to be hard-coded 32 words. So the CIP path was limited to the size of 32. This means that if an attacker would send a CIP path greater than 32 words, since the array of the CIP path was allocated on a stack buffer overflow will occur, and the attacker could potentially exploit it to remote code execution if they will smash the stack with their own data and jump to a shell code. And again, we're talking about old firmwares with no ASLR and DEP implemented. So this is a kind of a trivial memory corruption vulnerability. Attackers sending a CIP path larger than 32 bytes, larger than 32 words. And I was able to reproduce it. I was able to create my own exploit, reproduce it, and I shared it with Opto22. Now, if you look at the pseudocode that resembles this vulnerability, you can easily see that the data is being read from the packet, from the payload, and the stack or the array that was allocated on stack is being written too. So if we're overwriting more than the array, that's the array 32 words, then we're starting to overwrite the stack itself. And if we're writing more data on the stack, we eventually will overwrite the instruction pointer that will go back to the function, and we could achieve remote code execution. And again, I sent this exploit and this POC to Opto22, and they fixed it. Here you can see a very short example of how it would look like with random data. So we're sending, instead of 32 words, we're sending 64, and the first 32 words would be written to the array, and the next 32 words will be written onto the stack. So Opto22 fixed the vulnerability in their firmware. They thanked us. We had a very positive experience with them. But then we asked ourselves if this Ethernet IP protocol stack is proprietary to Opto22. Now, since I'm here talking about this, obviously the answer is no. It's an industrial or commercial Ethernet IP protocol stack. And we tried to understand what vendors are using this stack, what devices are using this stack, because we knew that Opto22 are not the only ones using this stack. And if we could exploit Opto22 devices, maybe attackers could exploit other devices using this stack. So after a long research, we came to the conclusion that this commercial stack is being created and developed by a company named Real-Time Automation. They call their stack 499ES Ethernet IP protocol stack. And we went on a mission to understand who is using this stack. So I have a question to you. How can we find who is using this protocol stack? Now, obviously, you should think about stuff like SBOM, software material, bill of material. But as you might be aware, it's not easy to get the list of third-party protocol stacks in firmwares, especially in SCADA domain. So what we did, we came up with a pretty clever solution. We came up with a fingerprinter, a stack detector that was able to query remote devices and look at specific attributes of the Ethernet IP protocol to determine what kind of protocol stack is being used. So what kind of specific implementation is being used? Now, you need to understand that whenever a company or organization is specifying, creating new specification for a protocol, they're not telling exactly how to implement it. They just telling some companies that develop these protocol stacks what guidelines that you follow. The protocol should support this and that functionality, but they're not saying exactly how to implement it. So it might be there are some differences, minor differences in the bits and bytes of the functionality of the protocol implemented that will allow us to differentiate between one type of protocol stack to the other one. So what we did is we looked at all the different attributes of the Ethernet IP protocol stack. What kind of differences could we see and observe from querying different functions in the Ethernet IP protocol stack? And I'll give you an example. So let's focus on the first one, Ethernet IP register session. Now, the register session is one of the functionality that Ethernet IP supports. So whenever we want to communicate with a remote device over Ethernet IP, we need to register a session. So we actually need to ask for the device for a valid session ID. Now, if we'll take this example of Rockwell Automation 1756 module, so we can actually communicate with the device and create a session. And this is part of the protocol. But what we noticed is if we'll open a session, close the session, open a new one, we will see a pattern in the session ID. So we will basically see that the session ID is being incremented in 100 hexabytes every time. So the first time we will get a session ID that is 4OF, and the next time we will get a session ID of 5OF, 6OF, 7OF, and so on. So this is a very unique feature or unique attribute that we can rely on to detect specific stacks being used by the 7056 module. Now, another example would be list services. So again, if we'll take the 7056 Rockwell module and we will query the list services, this is another functionality of the Ethernet IP, we will be able to get the capabilities or the services that this specific function by the Ethernet IP returns. For example, here we can see that the name of the service is communications with a capital C. But as it turns out, some implementations, some Ethernet IP protocol stack implementations return capital C, while others return non-capital C. Some returns 1 null byte at the end, while the other ones return 2 null bytes, just like in this case. So I think you understand where this goes. We mapped all different attributes and little changes that might be between different implementations, and we were able to build an Ethernet IP protocol stack detector. Now, how it works. So we listed all the different attributes that I just mentioned. Some of the attributes were easy to implement, some were more difficult. But eventually, we broke them down into kind of a Boolean flags, true or false. So for example, does the stack have this attribute of sequential sequence ID raising up in 100 hexa, true or false? Now, we had all of these attributes. I think we have around 15 different attributes that we were able to classify as true or false, like a Boolean flags. What we did out of them is mark them as 1 or 0. And out of the 1 or 0 hash, I would say, we were able to create a signature. So this signature identifies exactly this Ethernet IP protocol stack because it's very unique. It's very unique because it has this feature of raising in 100 hexa, and it has the communication with capital C and 2 null bytes. So all of these together create a very strong signature, like a hash that identify this specific protocol stack. So if we will scan another device and get this signature again, we will know that probably we're dealing with another Rockwell 1756 device, or at least a device that has the same stack, the same protocol stack. Now, how does it help us? If we'll take this as asset owners to our OT network, and we'll scan all the devices in our network. So for example, if we'll focus on the PLC and RTU there, we could easily map in just 1 second, just scan all the devices in the network, what protocol stacks, what Ethernet IP protocol stacks are being used, because we'll get all these signatures. We'll compare these signatures to the signatures we have in our own database, where we already mapped what it means that we're seeing a similar device to Rockwell 7056. And we could immediately tell the asset owner or the person that is using our protocol stack detector what protocol stacks are being used. So for example, RTA, Ethernet IP protocol stack. Now, we developed this tool. We released it as open source. You can download it from our GitHub repo. We actually sent it to a couple of vendors. So actually the vendors are using this tool to map their own devices, because not always they know what kind of protocol stacks they've been using for a decade or more, because they lost the code, they lost the contract, whatever. So you can download it and maybe open some issues or help us to maintain this tool. Now, back to our story. We scanned our lab with this tool. We scanned all the devices in our lab, and we do have a lot of devices. And we saw classes of similar implementations of Ethernet IP protocol stack. So we saw that all of these devices are using the same implementation, and all of these devices are using another implementation. And we use this, if you remember a story, to map what devices are using this exact same protocol stack as the vulnerable protocol stack that we found the vulnerability in. So currently, we're supporting a lot of different protocol stacks. For example, the RTA automation. This is our stack where we found the vulnerability in, and we also found other devices beside Opto22 that are using this stack. We also was able to understand that our stack support CPPO, which is used by Conpot, which is a great ICS honeypot, because again, the Conpot or the CPPO maintainers, developers use some specific attributes in the Ethernet IP protocol that we were able to specify, and now we can detect honeypots using our detector. And we also found another open source implementation of Ethernet IP named Opener, and we even found vulnerabilities in this protocol stack, but this is another story for another ICS summit, maybe next year. So back to our story again, we scanned our lab, we found many devices using RTA Ethernet IP protocol stack, and we started the party. We started a multi-vendor disclosure. So first of all, obviously, we had Opto22, we had discussions with Open22, we had discussions with RTA, and now we started discussions with ICS CERT and the other vendors that implemented this stack. So first thing what happened is that CISA or ICS CERT published an advisory about this protocol stack. We got our CVE, and then we started the multi-party disclosure. We had Opto22, we had ProSoft, we had FLIR, and we had other companies such as Bosch. They also published advisory, ProSoft, and other companies in Europe, United States, etc. That's it. Thank you very much.